Welcome to this explainer. Today we're putting on our detective hats to investigate a massive cosmic mystery. We are looking at a potential signal from an unusually low-mass black hole, one that according to the standard rulebooks of physics absolutely should not exist. You know, science is usually all about finding predictable, reliable patterns, but honestly, it's when those patterns completely break that we get the most mind-blowing, paradigm-shifting discoveries. We've got a cosmic suspect that totally defies standard physics, and it's up to us to piece together the clues and figure out exactly what's going on. Which naturally brings us to a huge question. What actually happens when we find a black hole that shouldn't exist? Well, an anomaly like this isn't just a glitch or a mistake. It's actually a doorway. It forces us to completely rethink everything we thought we knew about how black holes form and where they come from. It's a genuinely thrilling moment in science, as long as we're willing to follow the evidence wherever it leads. And get this, right now, we are looking at exactly one unusually low-mass black hole candidate. Literally, just one. Out in the vast, sprawling cosmos, finding a single object that breaks the mold is kind of like finding a needle in a galactic haystack. But that one signal, it's loud enough to make the entire scientific community stop in its tracks. Because if this single candidate turns out to be the real deal, it means our current rulebook is missing a massive, massive chapter. This whole mystery perfectly captures that old saying, the universe is stranger than science fiction. Reality just constantly outpaces our imagination. I mean, think about how we even spotted this anomaly in the first place. Humanity literally learned how to hear space-time. By using gravitational-wave astronomy, we proved that ripples in the actual fabric of space and time exist. We went from just theorizing about these ripples to building massive, highly sensitive machines that can actually hear the invisible echoes of the universe. And it's that exact mind-bending technology that just handed us this impossible anomaly. But okay, to really get why this specific anomaly is such a shocker, we first have to appreciate how far the science has come. Gravitational wave astronomy has officially leveled up. We've moved past isolated one-off discoveries and entered the era of population science. Basically, this is the study of broad patterns. We're talking black hole masses, their spins, and the environments they form in. Thanks to hundreds of detections, we aren't just staring at individual events anymore. We're zooming out, looking at the entire population, to map out the overarching rules of the universe. And looking at all those normal, everyday detections is absolutely crucial because it gives us a baseline. Yes, we proved gravitational waves exist, which was huge. But then we mapped out this vast constellation of hundreds of black hole mergers. That shift in focus let us see the broader cosmic patterns. And most importantly for our investigation today, it established the expected mass ranges for these objects. We finally know what a normal black hole is supposed to weigh. We have our baseline. So let's talk about those normal cosmic rules for a second. To spot the anomaly, you have to know the standard suspects, which in this case are ordinary stars. The typical way a black hole is born is intimately tied to the life cycle of a star. There's a very specific, well-documented playbook that dictates how a star lives, how it violently dies, and exactly what it leaves behind in the dark. It's basically a beautifully violent three-step process. First, you've got a massive star burning through its fuel over millions of years. Next, when that fuel eventually runs out, the star can't support its own massive weight anymore, boom, it goes supernova. And finally, the dead core that's left behind collapses in on itself, forming a stellar black hole. But here's the absolute kicker. This specific life cycle inherently limits how small the resulting black hole can be. A dying star can only compress so much mass. There is a strict, hard, lower limit to what we expect these things to weigh. And that brings us to the core of our mystery. Our new candidate is simply way too small to have been formed by that ordinary stellar life cycle. The signal we picked up completely defies the rules of normal stellar evolution. It sits way, way below that expected mass limit we just talked about. So, if it's too incredibly light to have been born from a dying star, how in the world did it get there? Who or what made it? This is where our cosmic detective work gets super exciting, because our main suspect just broke the fundamental laws of how we thought black holes were created. Just to put this into perspective, the disparity we are dealing with here is massive. On one hand, you have the absolute minimum weight a dying star can possibly produce, the expected stellar black hole mass. But then, you look at the mass of our anomaly candidate, and it is a staggering drop-off. The gap between what normal stellar evolution allows and what we might have just detected, it's not a rounding error. It's a massive chasm that ordinary science just cannot bridge. Since standard stellar evolution falls completely flat here, scientists had to come up with a radical hypothesis. one that requires a totally different, almost unthinkable formation mechanism. We literally have to look past the stars themselves. In fact, we have to look back to a time before stars even existed. We call this the primordial possibility. It's a hypothesis pulled straight from the absolute dawn of time, suggesting that the universe itself might have forged this low-mass object during its earliest, most chaotic moments. When you compare the origins side by side, it's honestly mind-blowing. Normal stellar black holes are formed from the collapse of ordinary, dying stars in our modern universe. But primordial black holes, those are hypothetical objects formed by massive density fluctuations in the incredibly early universe, long before the very first stars ever ignited. We are taking a gigantic conceptual leap here, from the violent death of a modern star all the way back to the incredibly chaotic, hyperdense birth of the universe itself. Okay, but let's pump the brakes for a second, because we need to keep our scientific rigor intact. As detectives, we have to clearly separate hard fact from theory. The confirmed science, gravitational waves exist plain and simple, and we have the evidence of hundreds of normal mergers to back that up. But our unusually low-mass object, right now, it's still just a candidate. And the idea that it's primordial is purely a hypothesis, which naturally leads to a lot of wild speculation about what this means for the cosmos. It's crucial to remember we're investigating an unconfirmed candidate that supports a theory. We aren't declaring a confirmed discovery just yet. Keeping that distinction crystal clear is exactly what makes the scientific method so powerful. But hey, let's indulge that speculation for just a minute. What actually happens if we find more of these? If this candidate is eventually confirmed, and if we prove it truly is primordial, it would drastically shift our entire understanding of reality. Finding a primordial black hole isn't just checking a box for a new type of space object, it's unlocking a brand new window into a part of cosmic history we have literally never been able to observe before. We're talking about a monumental paradigm shift. To really grasp why primordial black holes are such the ultimate prize, just think about the cosmic timeline. Mere fractions of a second after the Big Bang, those massive density fluctuations could have caused primordial black holes to form. Then, millions of years pass in total darkness before the first stars finally ignite. And then, billions of years later, modern stellar black holes start forming. If we can confirm this candidate, it acts like the ultimate cosmic time capsule. It literally holds structural data and echoes from a time before the universe even had light. It lets us reach back past the stars straight to the very beginning. Which leaves us with this absolutely mind-bending